Welcome to the 6th lecture on circles. In this lecture, we will be discussing the derivation of the common tangents to two circles. But before we start that, let us finish one of the topics that we could not cover in the last lecture. So, this is regarding the definition of something which is known as the director circle to a given circle. So, suppose that we have a circle with some center here at O and some radius. So, given a circle, so this circle is given to us, and then let us think about the locus of all those points which lie at the intersection of two tangents to this circle which intersect at 90 degrees. So, for example, let us say a tangent at this point, and then we have to consider another tangent to this circle which is going to be perpendicular to this first tangent. So, let us say probably somewhere here. So, we have another tangent here. So, we will make a perpendicular line to this normal. So, this is the other tangent, and let us say that these two tangents meet at 90 degrees. Then we are interested in the locus of these points of intersection. So, this is the point of intersection of these two tangents to the same given circle, but the tangents should be meeting at 90 degrees, should be perpendicular to each other. So, let this be point P. So, locus of all such points, and we can check. So, locus of all such points is going to form a circle actually, because if we have any such point like this point P over here, then clearly this angle is 90 degrees because this is the first tangent. Similarly, this angle is also 90 degrees, plus we are given that these two tangents are meeting at 90 degrees. So, obviously, if we look at this quadrilateral O Q P S, O Q P S, if we look at this quadrilateral, then three angles of this quadrilateral are 90 degrees. So, naturally, the fourth one has to be also 90 degrees, and therefore, this quadrilateral can either be a rectangle or a square, but then we see that OS and OQ are both equal to the radius of the first circle here that is given to us, and therefore, it is clear that OQPS has to be a square. So, what that basically means is that this distance is also equal to R, and therefore, the distance from O to this point P will be equal to square root of 2 times R. So, any such point P, so we can make another two tangents which are perpendicular to each other, and even so example we could have another two tangents, let us say tangent at this point like this, and then we need to have another tangent which is perpendicular to this tangent. So, let us say a tangent at this point over here. So, these two tangents meet at 90 degrees, and if we do a similar analysis like what we did for this point P, let us call this point as C. So, if we do a similar analysis, then what we will also see is that, so this is again going to be a square of side equal to R, and again this distance OC is going to be equal to square root of 2 times R, where R is the radius of the given circle. So, what we see is that any such point which lies at the intersection of two tangents which are intersecting at 90 degrees. So, any such point is going to be at a fixed distance of square root 2 times r from the center of the given circle, and therefore, the locus of all such points is another circle, because that was what was that was basically the definition of a circle, because each such point which lies at the intersection of two tangents which intersect at 90 degrees. So, each such point is going to lie at a fixed distance from the center of the given circle, and therefore, this circle that we get, which is the locus of all such points, is called the director circle to the given circle. And as we can see, the center of the director circle is the same as the center of the given circle. So, that is the first observation, that the center of the director circle to a given circle is same as the center of the given circle. That is one observation, and the other observation is that the radius of the director circle is square root of 2 times the radius of the given circle. So, with that we finish this discussion on the director circle. Next, we are going to talk about the common tangents of any two given circles. But before we do that, there is one little small result that probably would have been covered in one of the previous lectures, but we just bring it again here because in our analysis we will be using this result. So, the result is like this. It basically says that if we have a straight line over here whose slope is m and which passes through this point alpha beta. So, and then we have another point x naught y naught, and the question we are asked is to give an expression of the square distance, the minimum square distance of this point x naught y naught from any point on this straight line. So, obviously, as we know from high school, the shortest distance or the smallest distance is basically the perpendicular from this point onto this straight line, which is this perpendicular, and the square distance of this perpendicular. So, the square distance of this line segment from this point to this straight line is given by this formula. So, let us talk about common tangents between two circles. So, let us say that there are of course many cases here. So, let us draw any two circles here. So, this is the case when the two circles are neither touching each other nor are they intersecting each other. So, let these be the centers C1, C2. Then we can see that there are actually 4 tangents. So, 2 of the tangents, so 4 common tangents. So, what we mean by a common tangent? Common means that the same straight line is a tangent to both the circles. For example, let us say this straight line. So, this straight line that I have drawn is a tangent to both this first circle. So, this straight line is a tangent to the first circle at this point, and the same straight line is a tangent to the second circle at this point here. So, this straight line is therefore called a common tangent to both these given circles. So, we can draw another common tangent here. Like this. So, these two tangents are called direct common tangents. But apart from these two, we will still have two more tangents which are called transverse tangents, and they are like this. As we can see, this red line is a tangent to the first circle at this point, and the same red line is a tangent to this other circle at this point. So, in the case of a direct common tangent, both the circles are on one side of the tangent. If we see this, so as we know, any straight line divides the surface into two halves. One half is on this side of the straight line, for example, let us take this straight line, and the other half is on the other side of the straight line. In the case of a direct common tangent, both the circles are on one side of the tangent, on one side of the straight line tangent. Similarly, this is so such a tangent for which both the circles are on one side of it, that type of a tangent is called a direct common tangent. So, this green one is one of the direct common tangent because both the circles are below this straight line. Similarly, this other green tangent is also a direct common tangent because both the circles are above the or on one side of this straight line. But in the case of the red tangent, the red tangent obviously divides this surface into two parts, one is this side, the other is this part. And in the case of the red tangent, we can see that this bigger circle is on this side and the smaller circle is on the opposite side. So, such a tangent for which the two circles are not on the same side of the tangent is called a transverse common tangent. So, this is also a common tangent because this straight line is a tangent to both the circles, but then the circles are on opposite sides of the tangent. Transverse common tangent. So, there will be one more transverse common tangent, which is like this. So, in this first case, there will be totally 4 common tangents, 2 of them direct and the other 2 are transverse. So, in the next part of this lecture, we will see how to derive the equations of these direct common tangents, all the 4, and also the coordinates of the point of intersection of these common tangents. So, let us start with the derivation of the equation of the direct common tangents for this first case. So, let these be the 2 circles with center C1 and center C2, C1 has coordinates x1, y1, C2 has coordinates x2, y2, and let the radius of the first this circle with center C1 be R1 and that of the other circle with center C2 be R2. So, how do we suppose if we are given it is not, suppose the circles are not geometrically drawn and what we are given is only, let us say, the radius of these two circles and the coordinates of the centers of the circles. Then how do we check whether the case is that of two non-intersecting and non-touching circles? So, for that it is not very difficult. What we realize is that if the distance between, if the straight line distance between the two centers, so if the distance between the two centers, which is actually this expression, if this distance between the two centers is greater than the sum of the radius. So, this we can easily check. If this condition happens, then as we can see, if this condition happens, then it is clear that, because if we, let us say, if we join the centers with a straight line, then this distance is R1 from here to here and this distance is R2. So, obviously, if the two circles are not touching and not intersecting, then it is clear that the total distance between the two centers will be R1 plus R2 plus something more, because the two circles are not, neither are they touching nor are they intersecting. So, obviously, when that happens, this has to be true, and vice versa also. If the distance is more than R1 plus R2, then that also implies that they do not touch each other, or neither do they intersect. So, let us take this first case where we have two non-intersecting and non-touching circles. So, let us say these are the two circles. So, one has center C1, the other has center C2. Let the coordinates of C1 and C2 be x1, y1 and x2, y2. Let the radius of the first, this bigger circle with center C1 be R1 and that of the smaller circle with center C2 be R2. So, naturally, R1 is greater than R2 for this example here. Now, let us consider this common tangent. So, let the point of contact of this direct common tangent to to the first circle be at a point A, and the point of contact, or the point where this direct common tangent touches the second circle is, let that point be B. So, this is A, this is B. Clearly, these angles are 90 degrees. And let us consider the straight line joining the two centers of the circle, and let us extend that forward. So, clearly, this straight line is going to intersect the direct common tangent at some point P, whose coordinates we denote by alpha comma beta. So, our first job is to find the coordinate of this point P alpha comma beta, and then we shall find the equation of this direct common tangent. So, now this is R1 and this is R2. Now, let this distance between the two centers of the circle, let me denote it by L1, and let the distance between this point P and the center of the second circle C2 be L2. We observe that the triangle PBC2, which is this triangle, is similar to triangle PAC1, and this is because all the three angles of these two triangles, so PBC2 and PAC1, both these triangles have the same three angles, because as we can see, one angle is 90 degree, this angle is equal to this angle, and further it is clear that this angle is also common to both the triangles, and therefore, because two angles of both these triangles are same, the third angle also has to be the same, and because all the three angles are now same for these two triangles, it follows that both these triangles are similar, and therefore, from the similarity ratios, it follows that PC1, the length PC1 of the bigger triangle divided by the corresponding side length PC2 of the smaller triangle is equal to, so PC1 by PC2 is R1 by R2. Now, PC1 is nothing but L1 plus L2 divided by PC2 is L2, which is 1 plus L1 by L2, and that is R1 by R2. Therefore, L1 by L2 is R1 minus R2 upon R2, which implies that L2 is equal to L1 into R2 divided by R1 minus R2, and L1 is already known to us because the coordinates of the two centers are given to us. So, from here we should be able to find the coordinates of this point P. Now, the equation of so since this point P is lying on this straight line joining C1 C2, it follows that beta minus y1 divided by alpha minus x1. So, this is the slope of this line PC1. The slope of the line PC1 is this, and that slope is the same as the slope of the line C1 C2, because it is the same line anyways, and the slope of the line C1 and the slope of the line C1 C2 is and this in fact is also equal to the slope of the line PC2, which is beta minus y2 upon alpha minus x2. So, now we will try to find, so we already have got L2 here in terms of L1. Now, from here what we see is that this distance L2 is equal to, so L2 square let us say is equal to beta minus y2 whole square plus alpha minus x2 whole square, which I will take to the next slide. So, in the previous slide we had L2 square is beta minus y2 whole square plus alpha minus x2 whole square, which is equal to I will take alpha minus x 2 whole square as common outside, this multiplied by 1 plus beta minus y 2 whole square by alpha minus x 2 whole square. But beta minus y 2 divided by alpha minus x 2 is nothing but the slope of this straight line joining the centers of the two circles, which is actually equal to this quantity here. So, we can replace this here by the value. So, that implies that L 2 square is alpha minus x 2 whole square into 1 plus y 2 minus y 1 whole square upon x 2 minus x 1 whole square. But then from this equation here, we already know that L 2 square is L 1 square R 2 square by R 1 minus R 2 whole square. So, if we use this, then we equate this to be equal to L 1 square R 2 square by R 1 minus R 2 square, which is equal to, now L 1 square, L 1 is the distance between the centers of the two circles. So, L 1 square is, so this becomes R 2 square upon R 1 minus R 2 whole square into L 1 square is y 2 minus y 1 whole square plus x 2 minus x 1 whole square. So, this and this expression are equal, and then we see that we can take this as common denominator here, and then there will be something which is, and then what we, so this left hand side, this entire thing can be written as alpha minus x 2 whole square by x 2 minus x 1 whole square into x 2 minus x 1 whole square plus y 2 minus y 1 whole square, but this entire thing is equal to this, which is multiplied by this expression is the same as this. So, and then of course, we see that this and this are the same. So, what we end up getting is that alpha minus x 2 is equal to R 2 by R 1 minus R 2 into x 2 minus x 1, and if we simplify that further, we get the, so value of alpha to be x 2 plus R 2 into x 2 minus x 1 divided by R 1 minus R 2, which is R 1 x 2 minus R 2 x 1 divided by R 1 minus R 2. So, that is what is alpha. Remember, alpha was the x coordinate of this point of intersection of the straight line joining the centers of the circle with this direct common tangent. Similarly, we can find beta, and that is easy because we can use this equality over here, because since alpha is known now, we can easily find beta, and a little manipulation gives us beta equal to R 1 y 2 minus R 2 y 1 divided by R 1 minus R 2. So, now we have the coordinates of this point P, but our ultimate goal was to find the equation of this, direct common tangent. So, how do we get that? So, of course, one thing is that we know that this tangent lies on this point whose coordinates are known. So, therefore, if there is any point x comma y on this direct common tangent, then we can say that y minus beta upon x minus alpha. So, y minus beta upon x minus alpha is going to be the slope of this direct common tangent, and let that slope be equal to m. So, now if we know the slope of this direct common tangent, then we have finished finding the equation of this direct common tangent, because then this is the equation of the direct common tangent. But right now m is not known to us. So, how do we find m? Alpha and beta are known here, but m is not known. What we see is that, and this is where the very first result that we saw on the first few slides, which was about the shortest distance of a point from a given straight line. So, this is where this result is going to be very useful, because what we see here is that the shortest distance of this tangent from the centers of the first circle is r1, and from the center of the other circle is r2. So, this value of m has to be such that the shortest distance of this, because if the m is different, then the shortest distance might not be r1 and r2 from these two circles. But we know that since this is a direct common tangent, if you see this angle here is 90 degrees. So, this distance r1 is indeed the shortest distance bit of this center C1 from this direct common tangent, and similarly the shortest distance between the center C2 of the second circle and this direct common tangent is r2. But the m has to be such that, because it is clear, if we change the slope like this, then the distances will not be r1 and r2. I mean, I could have, for example, if I had the slope to be something else, then I would end up having a straight line like this, which passes through alpha beta. So, this black line also passes through alpha beta, but then since the shortest distance of this black line from the circle is not equal to, because this particular black line is not even touching these two circles, which means that the shortest distance from the center of these two circles to this black line will obviously not be r1 and r2, because if it is r1 and r2, it is clear that this black line has to be a common tangent to both the circles. So, we will use that to get some equation in terms of m and then try to solve for this m. So, we will use this fact. So, if we go back again in this figure, then the first equation that m should satisfy is that this particular straight line should have a distance equal to r1 from the point x1 y1. So, we are interested in, so if we come back here, we basically have a point which was the center of the circle C1 with coordinates x1 y1, and there was this direct common tangent whose line equation was y minus beta, or basically this particular tangent was passing through a point alpha beta. Then the shortest distance, the expression of the shortest distance from C1 to this common tangent passing through alpha beta has to be r1. So, now the shortest distance can be calculated using this formula. We have already said that the slope is m. So, the shortest distance will be equal to m times x1 minus alpha minus y1 minus beta whole square by 1 plus m square. So, this is the squared distance. So, this has to be equal to r1 square. So, this is the first condition that this m must satisfy, which is that, so this expression is for the shortest distance between this point x1 y1, which is the center of the first circle, and this direct common tangent, or rather this straight line having slope m and passing through a point alpha beta. So, that is what we had. We had a straight line having slope m and passing through this point alpha beta. So, we have calculated this distance, and the expression for the distance is this left hand side, but that must be equal to r 1 actually. So, this is the squared distance. So, since for this straight line to be a direct common tangent, the shortest distance has to be equal to r 1, and therefore, this expression for the squared distance has to be equal to r 1 square. And we will get a similar equation for the second circle, because the same straight line is also a tangent to the second circle. So, that is how we end up getting these two equations. So, this is for the first circle, and this is for the second circle. Now, if we try to simplify this equation, actually both these equations are one and the same. I mean, because and that one has to observe it a little keenly to see that point, because if we try to rewrite this, we can write it as x 2 minus alpha whole square into. So, I am rewriting this second equation, m minus y 2 minus beta by x 2 minus alpha whole square is equal to r 2 square into, or rather you can have it in the denominator, and this same thing can be written as m minus y 2 minus beta by x 2 minus alpha whole square by 1 plus m square equals r 2 square by x 2 minus alpha whole square. And so, the same thing we will try to do with the first equation. So, we have, so this is we have actually, so I will say 2 prime. So, from 2 we can get 2 prime very easily. Similarly, from the first equation we will get 1 prime, just doing it just taking out x 1 minus alpha out from here, will get m minus y 1 minus beta over x 1 minus alpha whole square by 1 plus m square is equal to r 1 square by x 1 minus alpha whole square. So, this is 1 prime and 2 prime was so this was 2 prime this equation was 2 prime. Now, if we go back just a few slides back, then we know that because, so this is x 1 y 1, this point C 2 is x 2 y 2, and then we have alpha beta. So, we already know that y 1 minus beta. So, y 1 minus beta upon x 1 minus alpha, which is this quantity, is nothing but the slope of this line joining the two centers of the circle, and similarly that slope is nothing but y 2 minus beta by x 2 minus alpha, which is this quantity, because this is one and the same straight line. So, the slope of this line segment and the slope of this line segment is the same. So, therefore, these two quantities are essentially the same only, and if that is actually also clear from here. So, this and this are the same. So, therefore, what we see is in both these equations 1 and 2, the left hand side here is the same. And now, what about the right hand side? It turns out that the right hand side is also the same, because if we recollect, then if we go back to the similar triangles, we see that R 1 by R 2 is equal to P C 1 by P C 2. So, if you remember, R 1 by R 2 is P C 1 by P C 2, which is equal to, which implies that R 1 square by R 2 square is P C 1 square by P C 2 square. Now, P C 1 square, P C 1 square is so, this is the expression for P C 1 square, x 1 minus alpha whole square plus y 1 minus beta whole square upon P C 2 square is x 2 minus alpha whole square plus y 2 minus beta whole square, and this is equal to x 1 minus alpha whole square into 1 plus y 1 minus beta by x 1 minus alpha whole square upon x 2 minus alpha whole square into 1 plus y 2 minus beta upon x 2 minus alpha square. So, y 2 minus beta square upon x 2 minus alpha square. Now, we have already seen that this ratio here and this ratio here are the same, because they are nothing but the square of the slope of the straight line joining the center of the circle. So, these two cancel out, and what we get is R 1 square by R 2 square is equal to this, and from this it follows that the right hand side of these two equations are also the same. So, we already had seen that the left hand side was same, now the right hand side is also same, and therefore, these two equations are one and the same only, and therefore, we need to only solve only one of these equations. We can take any one, it does not matter. So, we will only take one of these two equations and solve for m. So, let us take the first equation from where we had m minus. So, by S I will denote the slope of this line joining the. So, S is going to be the slope of line joining the centers C 1 and C 2. So, we get m minus S whole square by 1 plus m square is equal to r1 square by x1 minus alpha whole square. And we already have the expression for alpha. Alpha was r1 x2 minus r2 x1 by r1 minus r2, and therefore x1 minus alpha is that is x1 minus alpha is r1 into x1 minus x2 upon r1 minus r2. So, if when we put this equation back here, we get m minus s whole square by 1 plus m square equals r1 minus r2 whole square by x1 minus x2 whole square. And then if we rearrange this, what we actually get is a quadratic equation in M, which actually means that, and in this case there will be two real roots. There will be two real roots, but then what it means is that there are two different values of the slope, which means that there are possibly. So, once we solve this, we will get two solutions, we will get m equal to m1 and m equal to m2. So, let us say that this right hand quantity will denote it with k, because we already know r1 and r2, we know x1, x2. So, let us denote it by k. So, then what we have is, if we so we have m minus s whole square by 1 plus m square is k, and therefore, from that it follows that m square minus 2 ms plus s square is k plus k m square, and that can be further written as m square into k minus 1 plus 2 ms plus k minus s square equals 0. So, when we solve this quadratic equation in M, we get two solutions, M1 and M2, and therefore, we correspondingly get two straight line equations, y minus beta is equal to M1 into x minus alpha, and the other is y minus beta is M2 into x minus alpha, and both of these are valid direct common tangents. In fact, if we go back, then if we recollect our initial discussion, we had actually shown that there are actually two, in the figure we had shown that there will be actually two direct common tangents for this case, for the first case, and the slopes of these two are m1 and m2. So, the other direct common tangent will be something like this, and this other direct common tangent will also pass through alpha beta, and because that is clear from this equation, which means that this other common tangent is also going to pass through this point from the point P. So, essentially both the common tangents and the straight line joining the centers of the circles, they are all meeting at this point P. And further, there is one more, it is also easy to see that. So, these two direct common tangents meet at this point P, which lies on the straight line joining the centers of the circles, and this point P divides the straight line joining C1 C2 externally in the ratio of their radii. So, what I mean to say here is that So, this is the point of intersection alpha beta. This is the straight line joining the two centers, and we say that this point P divides this straight line joining the centers externally in the ratio of the radius, which means that, so what we are telling here is that since the division is external, what it means is that P C 1 divided by P C 2 is equal to R 1 by R 2, and that is something that we had already mentioned, and because I mean this clearly followed from the similarity of these two triangles. So, what this means is that this point P, where the two direct common tangents meet, divides the straight line joining the centers of the circle externally in the ratio R 1 to R 2, R 1 is to R 2. So, P C 1 divided by P C 2 is equal to R 1 divided by R 2. In the next lecture, we are going to derive the equation of the transverse common tangents to these circles, to both the circles, when both the circles do not touch each other, neither do they intersect each other. Thank you.